Sergei Winitzki, it's a pleasure for you to come on. Yeah, I came across you through your writings on joint calculus, because I was doing some research on how to do a what we call in the Erlang world the selective receive, and you, one of the major sort of authors, you've got blog posts going back to, I think, 2012 on the subject. So I pinged you and I thought it'd be really great if I could actually have you on, so to maybe you can give us an introduction into this subject. But the waters flow deep with you, because it's not only joint calculus, but you're a physicist too, and you've got a number of other things. So. Other things going on. So, so I'd love to hear your side of the story. Let us know.
Well, thank you for inviting me here. So I'm, first of all, I was a physicist for a number of years as a research physicist, doing purely theoretical physics. And then I essentially couldn't get a permanent job, and eventually turned to programming. So I became a software engineer. And then my first job was mobile development, iPhone and Android. And then by some chance, I looked at some papers on joint calculus, and I thought that it could be useful for user interface programming on the iPhone. Now, this may or may not actually be true, that it's useful. I don't think anyone is using joint calculus for that. But I thought there are so many bugs in the user interfaces that I'm having so much trouble fixing all those bugs. So maybe I need a better approach. I need an approach that allows me to program with fewer errors. So I started looking into joint calculus, and I implemented joint calculus on the iPhone as a library. And I tried to use it, and but I did not find it to be easy to use, and I did not find it to be useful for my job right away. So I abandoned that. But what struck me is that joint calculus seems to be a very nice approach to concurrency. It's not really theoretical. It's really very practical. The name calculus is deceptive. It is a programming language. It's not some kind of mathematical calculus. It's a programming language that allows you to write concurrent programs. So unfortunately, there isn't any readable description of what that language is. All the documentation that I could find that were completely unreadable for a programmer. And so I wrote my own tutorials, and I started to try to use it in some toy applications and to write down what I found. So that is where all that started. I'm not really well versed in the research literature, because the research literature is so theoretical that I don't find it very useful for a programmer to read all that stuff. So they are interested in proving that certain languages are equivalent to certain other languages or something like this. Well, a programmer is not really asking these questions. So the programmer asks the question more like, well, you know, how do I use it? How do I program my web service? Right? And the database. And I want to listen to events coming from the internet or coming from the user interface or something. So how do I program my user interface and listen to these events and make concurrent programs based on that in a safe way so that I don't have so many bugs? That is the programmer's question, and I try to answer that question in my tutorials.
Yeah, it was a sort of great introduction, because I read those initial papers. Well, the first one by, what's his name? Fabian. No, I think it's Fabian. I'm not sure. That was relatively okay, but there were a few other ones which were utterly unintelligible. Yeah. But reading your blog posts was actually quite enjoyable. But maybe you want to go into a sort of high-level description of what joint calculus is, and
Sure.
how it, maybe even how it differs from computation, other computation models. For example, like the typical lambda calculus that we are all too familiar with.
Yeah. So first of all, joint calculus is completely independent of a programming language that you use it with. So you can use it with any programming language, more or less. It's two features that you have to add to a programming language to enable concurrency. And one feature is that you have data that is somehow labeled as being concurrent. So the labeling is a special feature that you have to add. Now, this labeling doesn't have a good name in the literature. They call it messages or channels or something like this. It's very confusing. So one metaphor that they used initially was the chemical machine metaphor, the chemical simulation. The simulation of chemical reactions where molecules or atoms meet, react, produce other molecules or other atoms as products of reaction. And then in order to make a computation out of this, so you simulate reactions where each molecule carries some value on it, as if the molecule has a payload, which is some value in your programming language, maybe an array of some data or whatever. And then when the molecules meet, then they carry several pieces of data on them. And then you can write a function which is sitting on top of a reaction, of a chemical reaction, as if. So molecules carry data and chemical reactions carry functions. And the function takes as input the data that sits on the input molecules to the reaction. And the output molecules can carry out some result values, one or more result values. And so this function describes how the result values are computed given the input values. So you add, so this is the second feature that you add. Certain functions are labeled as these chemical functions or reaction functions or whatever you call them. And these functions are special in that they're called automatically whenever molecules become available with data. And molecules become available when you create this labeled concurrent data. So you say, here's my array of integers. Now, this array of integers is going to be concurrently labeled with molecule A. And when you say that, so this must be a feature of the language to be able to say that. You inject the molecule A into some virtual world where this molecule will wait for other molecules to react with. So this is one feature you add to the language. This must be some kind of special operator or special keyword or something that you say, this value X that I computed in my programming language is now not just a value X, is now actually floating on top of a molecule A. A molecule A is a, yeah.
Could I interrupt you? Could I liken it to be like an atom, or some programming languages refer to it as a symbol, whereby, like, for example, it's just like an arbitrary string, like a human readable name, but you can inject a typed instance into that atom. Yes. Can I say? Right. So we just call that a molecule, right?
Yeah.
And then,
well, they call them, yeah.
And then, so this molecule or this atom, I could say, gets injected into this reaction, as you said. And this is almost like, am I correct in saying it's more like it has concept of like a data flow kind of aspect to it? So as soon as those molecules become available, then computation immediately gets kicked off. So yeah, that's right. Now, how far am I off from this? In hardware, we have logic gates. We have, the AND gates, the OR gate, the NAND gate, etc. Now, the state of the gate, the output of the gate, changes once the inputs are of a certain value, but there needs to be an input. So in this sense, it becomes almost like hardware. Do you, how far am I
Well,
off?
there's one difference, is that in hardware you have a fixed number of gates. Here you do not have a fixed number of reactions. So you can emit any number of molecules that react, and they will all react possibly at the same time in parallel.
Okay.
So you can declare what molecules may react. For example, you can say molecule A reacts with nothing else, just by itself, it reacts,
Okay.
and it gives you molecule B. And then you emit a million molecules A with some data. So in principle, the runtime system will be able to start a million functions in parallel. Well, of course, it won't be a million in parallel on real hardware, but maybe 8 or 16 or 32 will run in parallel to compute the value for B and emit that value. And then once the 32 are done, then another 32 are going to be started. But all of this is implicit in the language. You don't start it yourself. You just say, I have labeled these data as molecule A data, and I'm just waiting for this to be done, so the reactions to be done. And then eventually there will be a lot of B's emitted. And there will be some intermediate time when a lot of A's are there and also a lot of B's are already emitted. It doesn't matter. I mean, this is, so in hardware, you will have a fixed number of gates. Here, you do not have a fixed number of gates. The gates are created as necessary. Whenever the data arrives, a new gate is created. You can think about it in this way.
I suppose also within the hardware world, the hardware world only has two types of molecules, which is high and low. But in joint calculus world, we have an arbitrary amount of different types of molecules. Is this correct?
That's true.
Yeah.
Yes.
Okay.
So you can define. So in your language, you need to be able to define any number of different molecules, A, B, C, D. You call them symbols. So you need to refer to them in some way.
Yeah.
In the programming language, they will be values. So but for debugging purposes, you could add some descriptive name to them. Right. These names are only for us to think about. They're not really affecting. So these names of molecules are not really affecting the computation.
They just need to be unique.
They need to be unique, and they need to be labels that are so. This is somehow just auxiliary for your convenience, but actually these are values. The function that emits molecule A is a value, and it must be distinct from a function that emits molecule B. That's it. So somehow you need to, for convenience, you need to label them with names, but essentially that's what it is. So in the programming language, you need to add this feature that you can emit molecules. You need to be able to define any number of them, A, B, C, D, whatever, with any names, and you need to be able to emit them. And of course, you define the type of data that they carry. So you say that a molecule A carries an array of integers, and molecule B carries a Boolean, and so on. It's convenient if you have a good programming language with a good type system, so that you can define your types well, according to your domain. But in principle, whatever programming language you have, you can just use this. If you have Erlang, you don't have types specified at compile time, or you can just add this to Python, for example, where you don't have types specified at compile time, but it doesn't matter. So if you have a programming language that has types, it will help to make your program less incorrect. And then you have this one feature. So the first feature is you define these molecules, and you should be able to emit at any time, should be able to emit them. Second feature, you define reactions, which can be combinations of any molecules you already defined. And then you have to specify a function that takes the input. So let's say 3 molecules need to come together. They have 3 values. So the function with 3 arguments needs to be written somewhere in your program and labeled, so that this function is labeled as the function that will wait for these 3 molecules. And that's what somehow you have to come up with a syntax for this kind of definition. Now, this is actually not easy to come up with a definition syntax for this kind of thing, because it's not a function that takes 3 arguments. It's a function that waits for 3 pieces of labeled data. That kind of syntax is not really available in programming languages. You don't have labeled this extra labeled data that is somehow coming. It's more like a pattern match, but it's not really a pattern match because you don't have the initial data in full. You're waiting for it to come. So it's not really a pattern match on a triple because you don't have a triple. Each part of a triple comes independently somehow. So you can try to come up with some syntax, and I did this in my initial implementation. Was very ugly in Objective-C. Then I had a number of years later, I had another implementation in Scala, which was much easier to deal with. Somebody else implemented this in Haskell. Again, this is all of this is just experimental work, and a lot of the questions remain, like what are the actual idioms and design patterns for this programming. But once you start playing with it, first of all, you realize concurrency is really in a different, it's seen in a different light when you do it like this. A lot of the concurrent programs are difficult because you're trying to manipulate shared state. In this paradigm, you do not have any shared state. So this is a little like Erlang, where you just have messages with data on them. And this select receive or whatever is the only thing that takes data out of the concurrent virtual world, and gives them to you. So you do not actually have shared data. You don't have locks, semaphores, and all that. I looked at a book. I think it's called something like the Book of Semaphores. It's a book that's full of examples and toy problems.
It'll turn your hair white, right?
Yeah, it is. It's all implemented in Python. So it's extremely hard to understand why a certain program works or does not work correctly. You know, you put a semaphore here. After this, you put that semaphore, and so it's just so hard to understand this. And there are mistakes that you can make very easily in this kind of situation, in this kind of paradigm. I went over a lot of these examples with joint calculus and re-implemented them. And I found that a lot of it is easier. Not all, but a lot of those things, you can kind of reason about the concurrency in a different way, not in the way of what happens to a value at a time when processes look at this value, and what processes run and how they wait for each other. No, you reason about data that is present or data that is not present. So you have to learn a very different way of reasoning when you write programs in joint calculus. You have to learn, or I prefer to call it a chemical machine, because this is a really what you need is a runtime simulator for this for these molecules, and this simulator is the one that you're working with. And then once you start thinking in terms of molecules that are present or molecules that are not present, that's the only thing you're allowed to think about. There are no processes that you can think about. There are molecules that are present or not present. So if you want something to run, the molecules must be present. If you want something not to run and wait, then this molecule should not be present. That's the only thing that so you have to start thinking about your concurrent program in a different way. That is a difficult thing to do. People have to change the way they think. People have to start formulating their problems in a different way, and so on. But this is the challenge. Maybe this is the reason why joint calculus didn't really take off. But it's not like it's unknown. A lot of people know about it in the programming language community.
So, Well, a number of things strike me. But first, like as a side note, I had a conversation with Peter van Roy, I think last Friday, and I brought up joint calculus with him, and he was like, "Ah, yes, the joint calculus guys." So apparently, like his group, the Mozart R's group, and the joint calculus group, they were actually they were the original joint calculus back in was it in the 1990s or something like that, round about that.
Mid 90s.
Mid 90s, yeah. Those two groups, they used to collaborate quite a lot. They used to collaborate quite a lot. So yeah, as you mentioned, you know, like people know about this. It's
oh yeah.
And okay, so that was just the side point. Now the actual question. This, what you described is concurrency that's sort of inherent within the program. So the underlying machine, it sounds like, okay, am I correct in saying, like, if you have a rather complicated program, you're essentially just, you could, in the joint calculus world, you essentially distill the entire source code or the DNA of the program to be a series of chemical reactions. So in essence, you wouldn't find many other typical language constructs, like, for example, you know, processes or threads, or yeah, you would have function calls, but that would be dependent within the chemistry soup process. But I mean, you wouldn't see many other sort of language constructs. I suppose you would have conditionals too, but now what I'm trying to, my question is this, that it seems like joint calculus, it makes a succinct solution to concurrency specifically within the application, but the underlying machine in current day hardware, we are now multiple CPUs, we're multi-core, we're actually distributed across networks and hardware. Like, is there a solution for joint calculus to go in a distributed environment? Like, for example, I have got something at the moment, but like, I want to sort of like, you know, put this this question out there and see like any ideas that you've got.
Right. So yeah, so there is an initial attempt to make joint calculus distributed, which is in the OCaml group that's implemented joint calculus on OCaml, which is still supported as far as I know. It's called JoCaml.
Yeah.
Right. It's a fork of the OCaml compiler to introduce special syntax to define molecules and reactions. Because OCaml itself does not have a flexible syntax facility. You cannot make easily a different syntax for a domain-specific language. Scala and Haskell do, but or C++ you can do that maybe, but not in OCaml. So they implemented a distributed facility where you publish molecules on a server or something like this, publish the names of the molecules on a server. Very difficult to use.
Sounds like it.
In a highly distributed setting, you would have to manage these published molecules, and it's very difficult. And what if, you know, a server is down? Yeah. You have to manage it yourself, and then, you know, network is down. You have to manage all the retries and all. So none of this is provided. I see two possibilities. I have thought about this some time ago. Right now, I'm not working actively on implementing distributed joint calculus. I started working on it, but time ran out for that project. Now, I will continue eventually. Two possibilities come to my mind. First possibility is when you want to have a one-to-one communication, secure one-to-one communication. So when your main goal is to distribute a lot of one-to-one transactions between a lot of different nodes on the network that are running different codes, but you have a lot of these one-on-one, very, very specific, focused one-on-one computations. I'm sending you something, waiting for a specific value in return. I'm checking that value, and then I agree with that value, approve it, and I acknowledge it, and you do the same. You also check my response and verify signatures cryptographically, and so on. Blockchain comes to mind. You have very focused transactions that are all verified one-to-one, one-on-one communication. So this is one way where you could say you need a facility to send data securely from one chemical machine to another, so that the other chemical machine will receive as if a new molecule from outside, but actually it isn't not a new molecule, it's a molecule that must be defined in this chemical machine, but the data comes from outside. So we verify that the sender is approved and the data is signed, and I don't know, security is verified, and then we allow this foreign data to be injected into our virtual chemical soup, and then we go on. So then we have this facility also to send molecules to third party, virtual chemical soup, and then we sign it and whatever, and we have our public keys. I don't know how, but we need to figure this out. So this is one scenario where you are focusing on this one-on-one secure communication. The second scenario is when you have a massively parallel data flow. So you have a million, matrices, and you need to do something with them, and it's, train some deep learning model on a distributed something, whatever. So it's a massively parallel computation. It's not a one-on-one communication situation. It's very different. You have a lot of data, and you need to distribute its processing among equally good nodes that all do the same thing. They all run the same computation. You just need a lot of them to run your computation quicker. So you distribute this data. Maybe you also want to verify, sign, but the point is these nodes are kind of just worker nodes for a large distributed computation. So your goal is to give them data to work on. If one of them fails, then give this data to someone else. Because you need all this data to be processed. You don't care that they fail. It's not a one-on-one transaction with that node. If that node is down, if it's not reachable, some other node needs to do the work. The work needs to be done. Once the work is done, you're done. So that is a different kind of problem that you're solving. And for that problem, what you need is an automatic distribution of the chemical soup among a cluster of computers, so that you don't even worry as the programmer about finding them, discovering, monitoring the nodes that are up or not up, or if they have succeeded or failed. None of this needs to be in your code. Your code needs to be the same. I have these computations. They are labeled as distributed. These molecules are labeled as distributed. Inject them, wait for the result. That should be your program. Now, the computations, of course, you described. Now, let me go back to your question about lambda calculus. The computations that...
Right. I got a question. Yeah, you keep going. Let me just write this question down.
Okay. So when you describe the computation that you want to perform, you need some kind of programming language, right? So joint calculus itself does not describe computations. It does not describe how to multiply matrices or anything. So you need a different programming language that you need to use inside your reactions. So your reactions are functions, but these functions need to be implemented in some programming language. The data structures need to be implemented. So this is completely orthogonal to the concurrency problems. So if you have any kind of program,
it's almost like a layer down. Do you see what I mean? So you've got the top layer which synchronizes on these atoms, the molecules, and then according to whichever one matches, then you unwrap, and then you have another computation layer, which could be the lambda calculus layer.
Yeah, it could be any programming language you prefer.
Right.
It could be, you can fall back onto your preferred programming language could be, JavaScript. It doesn't matter what it is.
Right.
I would be strongly against JavaScript, but if that is your preferred language,
man close to my heart.
You can... Right. I mean, I'm a functional programming fan and guru and whatever. And I'm certainly strongly against languages like Python and JavaScript for anything serious and
we'll go into that. We'll go into that shortly.
But
I believe there's a real axe to grind there.
Oh, I have. See, the thing is, it's not an opinion; it is the truth.
Yeah, right.
Now, the thing is, but nevertheless, so when you describe the reaction itself, it's just a function that takes input data and returns output data. And that function needs to be programmed in some language, and it doesn't matter in which language it's programmed. It's a sequential language that you need to use. Now, it's purely sequential computation. It can be very complicated, but it doesn't matter. So this is, from a concurrency point of view, it's just a sequential computation that can take a long time, and it gives output from input. So that is the relation to lambda calculus. If you want to use lambda calculus, you can use it. If you want to use, Rust, you can use it. If you want to use C++, you can use it. So that is the point.
Okay, so that
so there are two.
Yeah.
So let's go. So there are two possibilities where first you have a one-on-one secure communication between different agents, for which you need the specific facility of sending a molecule to a specific other address. I don't know how. So you can address by IP address, like what they did in JoCamol. You just have an IP address and you send the molecule there. Or you can address, I don't know, by Tor, network hash, or I don't know what. It doesn't matter. You have to decide what is your use case and what is your preferred way of addressing. But you have to identify this one particular agent to which you're sending this data. And then this agent will authenticate you and admit this data, and inject this data into their soups in some way, and then go on. And this agent will emit some other data back to you. They have to identify who you are, and then you will check their credentials and so on. So that is one situation for which you need to implement this additional functionality of sending a molecule to a specific external soup. You have to
like
identify
different syntax or semantics kind of thing. It might be like the Erlang style bang, which
it can be, but you have to identify somehow where you're sending. And you have to sign the data, maybe verify signatures. I don't know. So this is I'm not an expert in secure peer-to-peer networks and how to make them secure. I mean, I don't know the best solution, but there are some protocols and so on. And the second situation is when you have this massively parallel computation where you don't care about sending a message to a particular node, because what you care about is to get your million arrays, million matrices multiplied. And then which node does it, you don't really care so much. You need them to be there. So if for some time the nodes aren't there, you just wait until they come back online and continue. And all of this needs to be automatic. So your code does not need to do supervision, does not need to do error recovery, persistence. No, because you say, this is my data, it is concurrent and distributed, do it. And the runtime system needs to take care of this. And it can. You have systems like Zookeeper, you have systems like distributed databases. You can even do this with MySQL, because MySQL has some rudimentary facilities for time to live data so that you can do distributed locking. And I mean, this is really very basic if you want to do it like this, but you have to implement this runtime, and then your code will be extremely short code. Your code just says, my molecules ABC are distributed. Other molecules are not distributed, but these are. And my reactions, these and these are distributed, and others' reactions are not distributed. And so then, where is the cluster where I live? Now I have to somehow authenticate to this cluster, but once I authenticate, it's like a Borg world. I'm
Right.
assimilated into this cluster, and then there is no authentication anymore. There's no identity anymore. There's just molecules that float freely between all the minds in this cluster, and thoughts are freely exchanged, because nobody cares who comes up with the right answer. The right answer needs to be found. It is we now. It is not I, it is we. So this is how I would contrast these two scenarios, right? The scenarios where I and you, we talk. And I know exactly who you are, and you know exactly who I am, and you're not me. And I'm, or it's we. We have so much data, and it's all common. And if one of us sacrifices their life to the common computation, so much for the glory of us. So that is now, all of this can be implemented in joint calculus. All of this is possible, but it has not been done.
So I have a question regarding the Borg style joint calculus.
Yes.
At the end of the day, we're going to have some, this soup is going to be distributed across a number of nodes. Now, I assume there's some kind of a load balancer in this thing. So when one sends a molecule into this sort of like a collective soup, it will first hit the load balancer, then the load balancer will then make whatever the decision is, send the molecule wherever in the Borg individual is required. Now the question: assume that one of the individuals, I suppose, are you saying every single one of the individuals will have exactly the same chemistry, or would you?
Yes. Yes.
Aha.
Yes.
So it's a replication.
Of chemistry.
It's a replication of the chemistry across every single node.
Yeah.
And then you just load balance it accordingly.
Yeah. Yeah.
So what happens? What happens
what
happens if, okay, so assume everybody's got the same chemistry now, and to get a chemical reaction in any one of those nodes, you need molecules A, B, and C with arbitrary types in between. Now the load balancer sends an A to person one, node 1, molecule B to node 2, molecule C to node 3. All three of those are just going to do essentially, I'm not even going to say thread starvation. Shall I say data starvation?
It's deadlock.
Yeah, it's a deadlock.
If you do it this way, it's a deadlock. Now we need to do it correctly. If you have an A, B, the thing is, we know what the reactions are at compile time. We know that statically.
But the load balancer, that means load balancer now contains.
Maybe the load balancer should not do what you described. It should not just send molecules to nodes like that. It should understand that molecule A and B and C must be all together. So
okay,
they must
so it's a more evolved. Okay, so it's an informed load balancer.
Yeah. The load balancer must know the chemistry.
Right.
Only then you can it can decide that A, B, and C must be together sent to some node. You can do it the opposite way. You can let the nodes make claims on molecules. So one node says, I claim A, B, and C. And this claim will eventually expire if the node goes down, and then somebody else can claim them after that. You could implement it in this way. It doesn't have to be a load balancer of the kind you described. It just sends molecules one by one to nodes. So, but this is, like I said, it has not been implemented. So I don't know what is the right way that make it high performance. Right now, most data engineering is focused on streaming and not on this kind of arbitrary coordination. Now, this arbitrary coordination where you have A, B, and C, and imagine you can also have conditions on the values. So
so
A,
it's like
B,
a
and
dependent. It's a dependent type.
yeah.
Hang on. Okay.
No,
So
it's
no, I actually have a question regarding this. Because I was thinking,
yeah.
how does the dependency of value checking affect the chemistry? And does it introduce, what sort of problems does it introduce, and how does one go about doing that? Is
Right.
it currently the way it is now?
So there are different flavors of joint calculus that allow you different flexibility in what you can describe. So you can say molecule A always reacts with molecule B, no matter what values they carry. Or you can say there must be 2 copies of molecule A and 1 copy of molecule B, and only then they will react together. Or you can say there must be a molecule A with a value that is positive, and only then it will react to molecule B. And if it is negative, it will react with molecule C instead. So the question is, how much freedom do you want to allow the user to do this? Again, it is not known how to correctly provide. So the initial joint calculus, I think it provided a very rudimentary pattern matching facility where, for example, if a value is a disjunctive type, like option, or maybe in Haskell or something like that, then you're allowed to match on that value. And you're allowed to have different reactions if you have an empty or non-empty. So this is a rudimentary condition, but it is not a condition on the value, like an integer being positive. That was not allowed in initial joint calculus, because they didn't figure out.
But the disjunction matching, that's on the different types, or the sum type or the product type. But what I'm referring to, so within, are you actually talking about the actual value of the integer, for example? So maybe it's 42, and then you can continue.
Yes, so if it is 42, then molecule A with 42 on it will react with molecule B. You could write a condition like this, maybe.
What does that syntax look like? It sounds a little bit complicated.
Okay. Yeah, well, this is a different question, yes, but suppose you wanted this for your application, and you could implement. Now, I don't know if this is reasonable to allow this kind of flexibility. This is a lot of power and a lot of complexity for the runtime to understand which molecules can be put into what queue or whatever. It's a lot of complexity, which might not be reasonable. It might make the runtime very inefficient and yet not give you much expressive power. So I don't know, and I don't think a lot of, well, maybe some computer scientists have figured this out, but I haven't seen. So what
maybe it's enough to just match on the types. Maybe it's just enough to match on the types, right?
Maybe,
because then you got the type system which can describe enough of the program as it is. And
in the JOCAML system, the matching is performed using bit vectors. So in other words, the presence of a molecule is a bit in some bit vector. The fact that you have a molecule with a sum type, which part of the sum it is, it's another bit somewhere.
So that would be like Bloom filters, really.
Maybe, yeah. But you see, they are limited to this bit vector logic. So if you have a more complicated condition, then it's not a bit vector, not a bit anymore. You have to make a computation, and that's not supported. But this bit vector business makes the machine, the actual implementation of the runtime, more efficient. So then you can very quickly decide which reactions can start and which reactions cannot start. Now, this is a trade-off. I don't want to go very deeply into this because I don't know what is the right answer. Right now, I just say this is open. If you think you need this kind of functionality, so here's an example. The data needs to be cryptographically signed with somebody's public key. I want to check the signature. If the signature does not check, this data is not allowed, so the reaction will not start.
Yeah.
is this something that I want to express?
Oh no, that
Probably.
Yeah. Well, what I'm thinking about, that doesn't already happen. Like it won't even, like the data won't even be there because it's encrypted.
So
You
this
could
has
have to
be
decrypt
checked.
it, right?
This has to be checked at some other level.
Yes, at a lower level. Or yeah, or a higher
protocol
level.
At a protocol level, maybe.
Yeah.
So this molecule won't ever arrive.
It will never arrive. Yeah.
With the data that does not check.
Yeah.
Rather than arriving and then making the runtime of the chemical machine verify the signature with some arbitrary computation. So anyway, I would say let's keep it simple.
Okay. So okay. So yeah, that answers the question. And just on the point of the value, I think maybe the sweet spot would be just on the sum type matching. So if you deserialize the data, and it deserializes to be, for example, a sum or a none, then you can use that to go off to determine whichever type of chemistry bond you want to create, chemical reaction. Oh, that's okay. All right. Okay. So yeah, we've got into the distributed stuff quite nicely there. Now, how different is this a joint calculus from something called pi calculus? I admittedly, I don't really know too much about pi calculus, but it seems to be related.
So yeah, it is related. So pi calculus is more like the actor model. As far as I understand, you can have. So first of all these things, the calculi, they are very simple programming languages, which have not really been battle tested. So the point of pi calculus is that you have communication channels between running processes, and the process can wait until a message arrives in the channel. So it's kind of a mailbox where messages arrive one by one. Messages can carry data, and channels are also data. So you can put a channel on a message, the value of the channel.
The channel contains type data, right?
Yes.
But it's not data.
Well, in pi calculus, I'm not sure if they want types. You can always put it on there.
Okay.
You can always make a programming language that constrains the data to be of a given type. Okay. It's compile time. But I don't think in pi calculus they do it. But in any case, so the main thing of pi calculus is that you have running processes, parallel running processes, that can stop and wait until another process sends a message, and then it will go on. That is the main thing they do. They do not have any more than this. So you can start new processes, and you can specify what they're waiting for. So they're waiting for a specific message on a specific channel. Now, this message can contain data, which can be used later to compute something, or it could actually be a value of another channel on which you can send them. Because channels are values. So you can make a channel, and then you put that value of that channel onto a message, and they send that message to another channel. And then, so in this way, you can exchange information. You can send the message with a channel on which the reply should be sent, for example. So this is the main feature of the pi calculus. That's in a nutshell. It's communicating sequential processes. So you start these processes, and then this process will stop and wait until a message comes in a channel, and then it will continue. This is more like actor model in some ways, but it is actually limited. What is the difference between this and joint calculus? In joint calculus, you do not think in terms of running processes that stop and wait. In my view, it's harder to think about a state of a process that stopped and waited, and then something else comes, than to think about just data that is being processed, concurrent data that is being just processed and emitted back.
Or whether the presence of the data is there or not. Yeah,
That's
yeah.
right. It's much easier to think about that, about having or not having data, than about the several processes that run at the same time and may stop and may wait. And, you know, did I stop at the right time and wait at the right time for somebody else? And what is somebody else doing at that time?
Yeah.
And so on. Very difficult questions that are, anyway, but this is what you have to do if you program in the Golang, for example. Golang is an implementation of that paradigm, where you stop and wait and receive on a channel. So messages on a channel is a good metaphor if you have a single mailbox that only has a single linear queue, and you take messages one by one from it, and you can wait for a new message to arrive and so on. That is, joint calculus does not have this metaphor. It does not have linear mailboxes that wait one after another. All your data is simultaneously in the chemical machine. It is not in a linear queue. So you just put all of your data in the chemical machine.
So the program is the chemical machine. Chemical machine is the program.
Yes. So it is not that you're not thinking about what processes will be running at this time and what is the state of those processes at this time. You will be thinking about, do I have enough data to start this computation or not? And which process will provide that data? Did that process run already or not? Or does that process have enough data to run? That is what that's the only thing you think about, and not about the state in time of several processes that wait for each other. So this is a big conceptual difference between how you write programs. And I find that joint calculus is higher level, and the runtime is much harder to do right for joint calculus, to make it high performance. But in many cases, you don't want high performance. Your bottleneck is not coordination between processes. Your bottleneck is somewhere else, and you want correctness and declarativeness.
Yeah. So in the data flow declarative concurrency model, a variable data type can either be, it's a monotonic, so it's either unbound or it is bound. Once it's bound, you cannot unbind it. This is something that's present in something called Mozart Oz. Specifically, whenever you have like an equals, like A equals B or equals B, is it true or false? And only at that point will the values of A and B be calculated. So it's like this. So in this way, like everything is sort of like non-blocking until that point. Now, now what am I trying to say? Actually, I'm not even sure I have enough vocabulary to actually describe this. And if you don't understand this question, then we move on. But assume that you've got a CSP type environment, and you have data flow variables. Does this not make it more simple? So assume it's like a PyCalculus type environment with data flow variables. Would that make it more simple than just having pure normal?
Yeah, I'm not the right person to ask this question. Maybe Peter van Goor must be an expert on this. But the thing is, so yeah, when you have this data flow thing, in my view, this is completely orthogonal to processes. Data flow is not a process that you are simulating and that's waiting for anything. Data flow is a description of how one piece of data depends on another, so that when you need to compute something, you know what else needs to be computed. And then eventually you will compute it, starting from some given sources. And that is not a computation. So that computation can be concurrent automatically if you organize it, but it is not in the code. And the code does not describe that as a process. So if you add on to this the facility of receiving on a channel and waiting, well, you have combined two completely different paradigms So I'm not sure what you will gain. You will certainly use one or another for a certain problem, but I don't know how to combine them.
I suppose what I'm struggling with, well, I mean, maybe not struggling any longer, is that I'm seeking to make this project that I'm working on to be as declarative as possible. Now, so as you know, I'm implementing my own programming language, and I was using the Erlang model. Essentially, it's like a re-implementation of Erlang, but with data flow variables. And I've got this selective receive that's in Erlang, but I find it's rather it's not very declarative. But I found that the joint calculus model to be ever so much more declarative. It's so transparently simple how I want the computation to proceed given the presence of data.
Let's perhaps discuss the meaning of declarative.
That would be great. Let's hear your definition of that.
because a lot of people talk about things being declarative or things not being declarative. You know, you can say, well, everybody has their own definition, but I have my own definition, which is that declarative programs are those that are written in a way that is at the same time obvious to people, that the programs are correct, that they are doing what you want to do. And at the same time, they are translated into correct machine code. So here's an example. Most programming languages today have arithmetic facilities so that you can write x plus y divided by z plus 2 or something like this. Nobody tests this code anymore. You just write it. It's a simple formula, right? You are assuming that this will be computed correctly. You look at this formula, you know what is computed, so it's clear to people what needs to be computed. At the same time, there is enough understanding on the computer science how to translate this automatically into correct machine code, so that you no longer write unit tests. You know, x plus y plus z. Was the second plus allocated correctly? Right? Was it first? The second plus, did it free correctly after? No, you don't do this. You don't do this anymore. You just write. So this is an example of a declarative sublanguage. It's an arithmetic sublanguage, which is now part of every programming language, but it used to be different before the invention of Fortran, I believe, or Algo or something. I think Fortran was the first. People used to have a lot of trouble implementing arithmetic. It was a tedious job, but because it was not declarative. So what is now declarative? It is a language which mathematicians have come up with over centuries so that it is understandable and powerful at the same time to describe your problem, to describe the computation, and then it is automatically translated into correct code. So another example of declarative is SQL databases. You write something like select user ID from users where user status is logged in or something, right? It is obvious what it is doing. And it is obviously what you want. And yet it is translated automatically into the query plan and whatever, and you don't know what, and it will be done. So declarativeness means, in other words, it's a language that is somehow, well, first of all, people must approve of it. They must use it to describe to each other what they want to do. So if I want to, for example, I want to give you an example of where we don't have a declarative language today. If I want to describe to you some iPhone app, how to log in and how to change some credentials somewhere, it's a mess. There's no way that I can describe it to you clearly and unambiguously. I can provide you lots of screenshots, but they may not fit. They may have changed, right? There is no clear language that people use to describe to each other how they use modern user interfaces. So if I'm a customer and I want a user interface and you're a programmer, I don't have a clear way of communicating what I want. I can draw some screens, that won't be enough. I can talk about it, talk about what I want, won't be enough. I can tell you, well, after this window, there must come that window. And if that window is not there, then I must have this button or something. Okay, well, you can try to talk like this. It's not enough. There is not a clear, unambiguous, fully complete language of describing user interfaces, such that similar to the arithmetic, where I just write a formula and I'm done. This logic of what window comes after which button, and what happens if this window is big enough or not big enough, and so on and so on. It's hard. So what happens in reality, and I was working on this as a mobile developer, what happens is that a lot of iterations with customers, with testing, to figure out what the interface actually is. And then it's never documented. It's somewhere in the code. It's a mess. So that is an example of not having a declarative language, because we do not have a way of describing what we want from one person to another. And we don't have a way of coding it so that it's obviously correct. And that, you write this program, it's obviously doing what you need, and it doesn't have bugs, and it doesn't forget to deallocate some buttons or whatever. Here's an example. You know Slack, right?
Yeah.
Slack.
Burn it. Pour petrol over it and burn it.
So Slack used to have a bug where you start typing your message, your chat message, and then you turn your iPad sideways or iPhone, and then your message is gone. You're typing fresh. And then you turn again back into the original orientation, and your old message is back.
Jesus Christ.
Right? Okay, well, this seems to be a simple bug, right? There was a different buffer allocated for something at some point, and by mistake. So it shouldn't be a different buffer, it should be the same buffer. Okay, why was this bug made? Why was it made? It is because there isn't a clear way of writing your program so that it's obviously correct and what you want. There's no clear way of documenting your user interface somehow. So that is an example of not having a declarative approach. So this is my understanding of declarativeness. Let's go back to join calculus.
Wait, before you do that,
okay.
Actually, it's interesting that you brought up that very example, because this is something that this is a bit of a problem that I tried to tackle once with have you ever heard of something called flow-based programming?
I think so. I'm not.
Okay, so flow-based programming
is exactly.
Flow-based programming is in some senses rather similar to join calculus. Mix it with actor model. So assume you've got a graph of nodes, and then all of the nodes will take a typed input, and then depending on the combination, like it's a similar sort of a chemical reaction, in the sense that if there's an input on channel A and channel B, then the calculation will continue. So you can actually elevate above the internals of the component, and you can actually see the program as a graph. So I went to and we actually implemented this. But then I went a step further. I said, what if we could actually describe user interfaces by the manipulation of this graph? So you have, for example, a button component that has certain inputs, and which is connected to the canvas component. And I thought that would be one unified, simplified way of describing a user interface, but even that got so insanely complicated. It was just enough now, because there's fucking links everywhere. Oh, just too much.
Yeah.
So
well, yeah, but I can give you an example of a sub problem of user interfaces that was successfully solved by Apple, which is layout, the pure layout engine, which describes, so layouts are essentially trees of rectangles.
Yeah.
So there's a rectangle, a sub-rectangle, and so on. And it's a big tree of rectangles, and you have to describe properties and constraints on the sizes of these rectangles. So Apple has constructed a graphical editor where you draw all these buttons and labels and rectangles, and you specify constraints. This must be at least this wide, this must be half of that, and so on. And then you just turn it sideways and you take a look at what happens, and you change those constraints, and it just works. Now, why does it just work? They figured out what the system of constraint must be, so that there's always a solution. There's never the wrong solution. It's always quick to calculate. There's no, simplex method calculations necessary. It's always very easy quick to calculate your layout. So it's immediate feedback to the programmer what your layout is. In any, you can drag it, resize it, immediately see the results, and then you can easily. So this is exactly the declarative approach. You have declared what you want. You see it right away. You see right away if it's right or not, and then you quickly change. And there's no. Google failed to do that for Android. They do not have a similar system. Maybe they do now, but back then they didn't. In Google, you specify your layout superficially in a similar way. Constraints, this must be at least this much. This must be filling the container or whatever. The result is very often that your screen is blank when you run your program. So your graphical editor shows you something, but when you run it, you don't see it. Your screen is blank. Why is it blank? There is some constraint that interact with some other constraint, and the result is that the height of your entire window is 0. And then all your buttons are 0 height. Everything is there, but it's 0 height. So your screen is blank. But in the graphical editor, it doesn't show that. In the graphical editor, you see your buttons and so on. So this is a failure of declarativeness. You declared that you wanted your buttons. You see them when you declared them, but this is not translated into correct machine code. Very hard to debug in this situation because you don't know where the error is. You declared what you wanted. So what did you declare wrong? Should I not want something there? You don't know. So it's a hard situation to debug. You go one by one, what you added, what you removed, try to go back to the previous working configuration and try to guess what went wrong. Well, you added some constraints somewhere which interacted in an unforeseen way with another constraint. And the result is that the constraint solving engine made everything equal to 0. But you did not see that when you were designing. So that is a failure of being declarative. And so at least this, you can easily see what you must strive for when you want to have a declarative language. So your program must read unambiguously and obviously correct. X equals 1, Y equals X. It must be obvious what Y is, right? It must be also 1 at this point. Now, if this is not true, it is a major loss of productivity for everyone. So declarativeness is what makes programmers a lot more productive. But it's hard to achieve because you need to know this language that is at the same time understandable to people and to computers. So how do you come up with this language? That is the main question. This language is not easy to come up with. And so for some domains we have them, and for other domains we don't. And the domain of user interfaces is hard Maybe it has, temporal aspects, what happens after what. There are animations that take time. There are events that can take time or arrive at any time. It's not easy to specify that. There might be temporal logic necessary to specify them. Maybe something else is necessary. So haven't yet figured out that. But so if you are interested in designing a declarative language, what is joint calculus declarative for? It is declarative for this kind of computation where you have resources that are consumed. Like molecules, they're resources, they're consumed or created. And without this resource, you cannot start. And with this resource, you must start. You must start. So is this a situation that you are in? Does this describe
exactly
kind of the situation that you want to program?
That's exactly the model. Although it's targeting to be a secure environment whereby, for example, remember you said there's two different sorts of distributed models. Well, what I'm building is the first version. So we don't address now assume we've also have these lightweight language thread processes similar to Erlang, but within these Erlang messages, they share no state with other processes. The only way to communicate data will be via message passing. Now, addressing how one process will address another process is via the public key of that process. And with now with that in mind, so now I can actually do encryption decryption within the process itself, so that the process will then fully acknowledge that the data is actually coming from that process or from you, for example. And secondly, everything and this one important thing I want to make, because it's a secure environment and I have to be able to know who I'm talking to before I start up a process. I need to tell the chemical reaction, part of the chemical reaction, I need to insert state into this chemical reaction to say, okay, chemical reaction A, B, and C, and D, whenever we'll call that for the first one, you can only do this once, for example, A comes from person X, B comes from person Y, and C comes from person Z. Because within this environment, the identity of the other actors or the other processes is mandatory. So, but then I'm also in an environment because but this makes the environment rather, how can I say, constricting, because there are certain situations whereby you want to have a message from anybody. For example, let's say you're running a shop and essentially what goes on behind the counter, we can say is a deterministic process, right? You get somebody comes in, they want a sandwich. It's essentially a deterministic process on the creation of that sandwich. But we don't know, like anything in front of the counter, we don't know the identity of who's going to come. So as a business, we want to be able to service anybody. So this language should be able to express but it must be explicit. It must be an explicit thing to say, this chemical reaction will accept this molecule from anybody. And so along these lines.
But for example, I could just to throw in an idea. A molecule comes from outside, or rather the data for this molecule comes from outside, from anybody.
Yes.
But the data could contain an identity of a certain addressee to whom now some output must be directed.
Yes, it's possible too. Yes.
So but that would be kind of part of the data that is carried on this molecule.
Yes,
that comes from anybody.
Yeah.
Or you can say, I want now to know the identity of this sender, and this identity I want to read from this molecule somehow.
Oh, okay. Yes, I can do
came
that.
From
yes.
the sender.
Yes. Yeah, that's possible to do.
I don't have to put the data explicitly always on the molecule, but anyway, this is.
I can send an empty molecule. I can send an empty molecule.
Yeah, and then you just read the identity from it.
Actually, you've given me an idea now. I think you've given me a bit of an idea, because you described the idea of process calculus, whereby you can send a channel to somebody else and they can accept data. Well, in this model, you can send, okay, in the programming language I'm developing, the concept of who is a first-class citizen. So the public key is a first-class citizen. It's an addressable first-class citizen, which, okay, so now I could actually put that inside one of these molecules. I can send that to you and say, don't respond to me. Respond to whoever's in this in the payload.
That's right. That's right. Yeah. You could, yeah.
This is okay. You've
yeah. That's
got
I mean,
me
you could just
yeah.
say every molecule that comes from outside knows the identity of the sender. Yeah. Automatically.
Yes, they do.
So if you want to just reply to the sender, you can.
You can.
But you can also reply to an arbitrary other entity if you know their public key.
Yeah. So, well, this is we've done some interesting deep dive into joint calculus, and I think you've actually given me some great inspiration. I really appreciate that. But you did mention earlier on about functional programming. It'd be really interesting to hear. And I know that you're the author of a book that is not yet published. Is that right?
No.
Shall we dare to open the functional programming book? And
yeah, well, I can very quickly. I don't want to go into details here. It's not the right place. I can explain what it is about. So functional programming, first of all, is a very different paradigm than other paradigms. There are paradigms like object-oriented logic, constraint programming. There are these paradigms, right? So an example of constraint programming is LaTeX, where you write your text and you say how it is constrained to fit pages and so on. You don't actually say on which page anything will be, like you do in Microsoft Word. You say, well, this must be of this size, but how you format the words, I don't know. Format them in the best way possible. And so this is now functional programming is a very different paradigm from these, because there are mathematical theories that help programmers write code. In all those other paradigms, there are mathematical theories that explain how programs work, but they do not help programmers write code. If you're thinking about a logic programming, Prolog, for example, there is a beautiful mathematical foundation of how the program works. Logical clauses and resolution and all, proof, but it does not help you at all to actually program.
Horn clauses, I think it's horn clauses, isn't it?
Horn clauses, yes. Right. Horn clauses. Thank you. So that is, mathematically beautiful and rigorous, but it does not help you in any way to write Prolog correctly. You write Prolog by trial and error. Actually, it's quite imperative, and it's hard to do. Programs are short, yes, but they're hard to write. So the programs are written by trial and error, by kind of experience. And I came up at some point with the understanding that this is how artisans work. They work by trial and error, by experience, by tradition. They learn from others by imitating what others do and changing that a little bit to make it a bit better, right? But engineers work in a different way. So if you were actually a software engineer, like a mechanical engineer or electrical engineer, you wouldn't work in this way. You would, first of all, open up some math program that will give you a design and check some equations for that design. Right, like a bridge, you will calculate if the bridge falls or not, and so on. I'm oversimplifying, obviously.
No, it's true. They've got these things,
right?
Airplanes, right?
They've got airplane. They got these CAD programs, computer-aided design, which do simulation, and mathematical numerical simulation of airflow or whatever. Before you start constructing your device, you do calculations that tell you what will work and what will not work. If you can if you want to make an antenna, then you have the sizes and the frequency spectrum and blah, blah, blah. And you just do some calculations. Maybe it's standard now, you just have some programs that do your calculations, but you do calculations. And these calculations tell you what to do and what not to do.
People have actually applied evolutionary algorithms, EAs, to actually derive like the most efficient sort of antenna, for example. It's really interesting, the shape of that thing.
Yeah, you can try to, because there is a mathematical theory that guides your development, guides your design. Functional programming is the only paradigm right now where there is some amount of mathematical theories that guide your designs. That they tell you, for example, which types to use for your data. If your data needs to have certain properties, these properties are formulated in a mathematical way, and the types are guaranteed to work in this way. There is no other paradigm that does it. So in other words, if you use functional programming, you a little bit work as an engineer. If you use any other paradigm, you work as an artisan. It's not like artisans are somehow bad or inferior. Artisans are great, very, very, very good, but you just cannot do complicated stuff in an artisanal way. You're overwhelmed with the complexity of software. Yeah.
Games programmers, that's massively, massively complicated stuff. Yeah, and a lot of them, it's a non-starter to implement these modern day graphical sort of games within a functional programming language. It's quite no.
Oh, you're asking a different question.
Okay.
Right? You're asking, do we have today systems of functional programming that are adequate for certain tasks? And of course, we may not have them. So game programming needs to squeeze out every ounce of performance out of a little chip. And yeah, you're not going to use very beautiful formalisms there. You're going to write very ugly code, which will be very hard to write. So it's artisanal all the way.
I see.
Very difficult work, yes. I'm not saying it's somehow wrong or bad. I'm just saying it's a different kind of activity where there is no theory that guides your designs. Now, there is theory, for example, about three-dimensional graphics, how to draw three-dimensional graphics. But it's different. It's not how to write code. That is what to compute. That is a mathematical theory about what you want to compute. How you write code for that, mathematics doesn't tell you. Machine learning, very similar situation. There are lots of mathematics telling you how to do this and that, but it doesn't tell you how to organize your code. So they're all artisans when they write code. Functional programming is the only one where you can have mathematical questions with rigorous answers telling you that this code will work and this code will not work. And before you write code, it's not the same as verifying programs, proving correctness. It's not the same, because proving correctness means somehow you already written your program and then you prove its correctness. How did you write it? Donald Knuth wrote big books with a lot of math in them, but all these books are about how Donald Knuth can guess correctly the sequence of assembly language instructions. And then Donald Knuth can prove that this is correctly guessed. Donald Knuth is very, very experienced in this kind of guessing. And so, and he can prove things very well. But that's it. There is no theory that helps me to do that. Maybe I'm not as smart as Donald Knuth. I do not guess very well. So what do I do? Now, functional programming, for example, it tells you that if you want to write a domain-specific language where you want to define variables inside the language, and then you continue computations after having computed some value in this variable, then there is a way of doing that with well-defined properties where you use a so-called monad. And this is actually, it's a so-called free monad. Oh, doesn't matter what it is. Right now, there's one chapter left in my book to be written about free monads and free functors and free other things. This is a specific mathematical construction which tells you what types to define in your code to guarantee that you will have correct functionality in certain ways. This kind of thing is just not available in other paradigms. You cannot prove that in advance that certain data types will be right and others will not be right. Rust, for example, is a language where you have sum types and product types and function types at the same time, right? In languages like this, sometimes you have difficulty understanding the types and what they actually do and how to combine them. And some of these questions can be answered rigorously. It's not a matter of opinion, experience, tradition. It's a rigorously mathematically answered question. For example, I want to combine this type constructor with this type constructor. Can I define a map function for the resulting type constructor? Right, the map, you know, the map function, right? Like
yeah,
for a list,
yeah.
the map function will apply some transformation to each value in the list and make a new list with that. And now this is a map function standard. And map reduce, for example, is a style of programming where you have functions like this and you program with them. The question is, can I define map for my data structure? Not for a standard data structure like an array, but for my data structure, sums, products, functions, maybe, whatever. How do I do that? Do I know that I did it correctly? The interesting thing is that there is even a question like this which can be answered. There is a single correct way of implementing a map function for a custom data type. And there are maybe many other incorrect ways, and these incorrect ways will bite you if you use them. So don't use them. And this is mathematically rigorous. So I started, well, let's go back to my book. I started looking into functional programming around 2009. I understood nothing. I thought it was weird, useless. You know, who would ever do things like that, and why? And you know, I like recursion, but why? You know, other things are just, and of course monads and all that. So the first thing you notice is they start talking about monads and functors and I don't know what else. And the more you look into that, the more stuff you seem to need to learn. And then what is this? So I was kind of intrigued. Then I realized actually it is because functional programming is more like engineering. Because you need, if you look into a book on electrical engineering, you will find, you know, delta functions and Fourier transform and Z transform, you know, Z transform, and you know, and here you have lambda function and you know, something continuation passing transform. I don't know. You have to learn this because it's useful and because you're actually using it in your designs. So then I found that there isn't really a book or a tutorial that explains this at the level that I want. For example, monad. I don't know how much you know about monads. I don't want to
Oh no,
put
no,
a lot of
no.
load on you here.
To me, like that's just like transitioning state. But that's like a Haskell concept, and I stay away from Haskell.
Sure, that's okay. Well, I just want to give an example of why I was not satisfied and why I decided to write my own book.
Okay, so now this book that you've got, is it like a pre-release? Is it, can I go on to, where can I get it? Because the reason why is the way you've described that has sort of like piqued my interest, because you explained joint calculus so well. So maybe you're going to do a great job at being able to explain.
Yeah, I certainly I try to explain, because I find that there isn't enough detail and explanation in academic sources, at least. Academic sources are not very good for programmers to read. But yeah, you can, so the entire book is open source on GitHub. There are PDFs automatically built from the master branch that you can download. Right now, all chapters except one are done. Well, of course, I might edit some more after finishing that one chapter. But essentially, the material is going to stay as it is, and I'm not going to change anything very much. Maybe some wording somewhere. So yeah, you can. I'll send you links to this. You can put them in the video.
In the description, I'll put in the description below.
Yeah.
For folks to check out.
Yeah. So an example is about the monads. So there's, for example, a book just published last year, I think, called The Book of Monads. So I'm going to explain to you all about monads. Great. So this book explains quite a lot about monads. It doesn't have a single proof that what is in this book is correct. Although it claims that this, there are laws that monads must satisfy. There are mathematical equations which must be satisfied. These laws are written, but they're not proved, not in a single example. That, in other words, either it is somehow too difficult to write that proof, or because when you're a new person getting into the field, you don't understand what is going on. So there are some laws. Okay, what if I violate these laws? What are the consequences? Is my program going to crash or what? And if I implement my monad not satisfying the law, what will happen? Okay, now you give me this, you mentioned in Haskell a state monad, a state transition. Okay, well, you give me the code for this monad. Does it satisfy the law? Show me. Nobody does. You won't find a single tutorial on the web that proves that state monad, that code of the state monad for transitioning from one state to the next, satisfies the laws that supposedly every monad must satisfy. Now, this is a piece of mathematical derivation which needs to be done. It's not easy for somebody who is not well acquainted with algebra and mathematics in general, somebody who did not study calculus, for instance, somebody or higher algebra, right? They don't have the experience necessary to even understand how to do that, how to write what is to be written. Why is that a proof? How much is a proof? How much do you have to write to prove something? They don't have this experience. Most programmers don't have this experience. And so, okay, but to me, this is an important question. I'm a physicist by education. I have that experience. I have written a lot of calculations in my research. So I'm able to do that. What are even the notations for this that are useful? How do you even prove this? This is what this book is about. But at the same time, I'm a little skeptical of the academic approach to functional programming, which is prevalent in many communities, which is that let's go as far as possible into pure mathematics, talk about that as if we are discussing code. You know,
I've noticed that quite a bit in the papers. So actually, you're going to take this down from a different perspective. I think it's going to be fascinating to read. Are there any other books remotely like what you're doing?
Yes, there are, but not at the same level, not from the same perspective. There are books that try to do the same. So one book is called Functional Programming in Scala, and it does go a little bit in this territory, and even in terms of proving things and showing how to prove, but it has by far not enough detail and not enough explanation. It's very hard for people to get into that, but it's a very good book that actually taught me a lot of this stuff. And then I had to ask these questions and understand really what is going on. And then there's another book called Program Design by Calculation. And that book is trying to do a similar approach, but they're different focus. My focus is more on what is the least amount of theory that an engineer needs in order to answer all the questions that we have in the code. So in the code, we have a question like, why is this code equivalent to this one? How can I refactor? Why is the refactor incorrect? I want to prove mathematically that it is correct. What is the mathematical theory necessary for that? And no more. I don't want to go more into abstract mathematics than this. If I can avoid some mathematics, I will. And actually, there is a lot of mathematics there, which is not useful. Yeah. It is kind of popular. They talk about it a lot, but it's completely not useful. It's more almost they're showing off. You know, I
agree
know
with
these
you.
words.
There's a lot of that. There's a lot of that fucking showing off, eh? Oh,
yeah. I know all these words, and you don't. And so there. But,
we're not
but
little
actually,
yeah. Mm-hmm.
But actually, if you suppose you learn all this, you would have wasted your time. You don't, as a programmer, you would have wasted your time. You don't get any use. So my book is trying to focus on that which is demonstrable to be useful. So that is a different perspective than many other books, and yet it is a theory book. There are like 400 pages of math in there, which you know, I'm pretty sure that nobody will read like everything because it's just too much. But I try to first do practical section to say what we want as programmers, and then what are the questions that this leads us to.
Right.
Like, why is this correct? Can we prove that this is correct? Can we do the same for different data structures? What are all the possible data structures for which this works? And so on. And eventually the questions stop. And that's, you know, very, very nice in my view, that it's a natural stop. So, you know, for example, MapReduce.
Yes.
What are the questions that you ask as a programmer about MapReduce? Well, there are certain questions. Let's answer them. When we have answered them, let's stop.
You know, you actually. So just as an example of you saying that functional programming, or along with the certain types, it brings you a step closer to engineering. When I understood product type and sum type, and how, you know, the match along the different, basically it's the equivalent of product type and sum type are such bad names, but I mean, this is an example of that shitty naming stuff. But really, it's basically or and
right.
For data. And when you see it from that perspective, then the match statement or the case statement just goes through the different different types of data, like on an OR axis, and then the AND is the combination thereof, then your computations and the code actually looks rather more simple. So now with that in mind, I really do think I should, because I'm implementing a functional programming language, it now makes a lot more sense to me to actually go read your 400 pages just to sort of like get to the nitty gritty, even if it's just to increase the understanding.
Well, you can try to look for books that explain, for example, how to implement Lisp.
I've done
or
that.
How to implement. Yeah. Okay. So that is maybe. Anyway, I'm certainly in favor of somebody reading my book. The thing is, it's big, and eventually it will become not necessarily what you want, but certainly there is a lot that everybody could take out of it at any level. I try to go from, in each chapter, I go from practical usage code examples, and that informs me about what questions I want to answer from the theory point of view. But this is a theory book, so nobody writes this. Nobody's interested in this. Academics aren't interested in that. From their point of view, all questions are already answered in this area. There isn't anything to be asked, because they are not interested in questions that programmers have. Programmers, at the same time, are intimidated by all this language and all this complexity. You're supposed to know category theory. You're supposed to know proof theory. You're supposed to know type theory. What even is type theory? So you are supposed to know all of this, but actually that is not true. That is not true. All you're supposed to know is what's in my book.
I love it. So on that note,
Okay.
So I mean, as you were going to say, sorry, I was thinking, because like we've sort of got like like a 20 minutes left before, because you mentioned there was just like 2 hours that you had, so maybe we can use it to sort of wrap it up, or do we want to touch up on any other subjects, or just an easy wind down type of thing? I'm not sure.
Yeah, well, let's see. So I'm right now trying to use all my free time, which is, I don't have a lot of free time as a toddler.
Thank you very much for this time.
a lot of time. Like today she's in daycare. That's why we can talk. If yesterday she had high fever, I would have to cancel.
Yeah, but the little monster's coming home soon, so
yeah. No. So that's one thing. I'm planning to implement the joint calculus in the Borg style.
Ooh. So we're going to have competing implementations. We're going to have the individual, and then we got the Borg style. That'll be quite interesting if the two universes can merge. Picard will be assimilated.
Yeah, I was not thinking about the kind of secure one-to-one communication exchange style. But you could combine the two. You could have a secure communication between Borgs.
Yeah, I was just thinking that actually.
Yeah, so you can do Borgs, which are able to do a lot of massive computation, massively parallel computation, but they securely authenticate with other Borgs, which could be just one node. It doesn't have to be massively parallel. Now, it's not easy to come up with an efficient implementation. I'm trying to think about it, but like I said, I have very little time right now. I'm mostly focused on finishing the functional programming book, where I probably need another several months to finish at this pace. But after that, I'll come back to my joint calculus projects for sure, because I don't think anybody has figured out how to do it efficiently. Maybe my implementation won't be efficient, but it's okay. As long as it works correctly and I can run, for example, distributed chat or or something like this, because you could use joint calculus even for things like distributed chat, and you could do that. It's not necessarily going to be declarative anymore, because you're trying to shoehorn into this mode of resources on molecules. You're trying to shoehorn into that a problem that is more like broadcasting information, or waiting for replies and getting, finding out who's online, for example, right? Things like that for chatting. You find out who's online and you start chatting with them. You have to somehow reformulate into this language of resources that are consumed. It's not necessarily going to be declarative. So, like in the way that I described. So, do you know the dining philosopher's problem, right?
Yes. Yes.
Yeah. So for dining philosopher's problem, joint calculus is exactly declarative. You can write the solution, because for dining philosopher's problem, it's a resource allocation problem. So you need 2 items for something to start working. And that's exactly what you declare in the joint calculus. You need molecule A, molecule B, in order to start something, and they will be consumed. So this atomic consumption of resources is exactly what the difficulty in the dining philosophers is, but it's already solved for you by the runtime of the joint calculus. So it's exactly the declarative definition for that. Now, can you always reformulate, say a concurrent user interface, or concurrent database, or concurrent something else? Can you always reformulate that in terms of some kind of dining philosophers, where you have resources to be consumed atomically and synchronized on basis of that? I don't know. So this actually, let me mention one more thing. The creator of the Scala programming language, Martin Odersky, has worked on joint calculus. At least 3 of his graduate students, he's a professor at
EPFL.
EPFL, University in Lausanne. At least 3 of his graduate students have worked on joint calculus and published on it. And you don't see any trace of it anywhere in Scala, in the Scala language, or in, they never mention it. They essentially never mention it. Some of his graduate students have become themselves professors somewhere else. They're not working on joint calculus anymore. It's weird. They all know it, but nobody talks about it. It's as if the time hasn't come. Well, let me give you another bit of trivia. So I made a graph at some point. When a certain idea was invented in computer science, and when this idea was widely adopted by the industry.
25 years?
40.
Yeah.
Well,
yeah.
I have a linear regression actually through that graph. A very good linear regression with about 38.2 years of delay. So 38.2 years, and you're golden. But so you need like 1995 plus 38.2, right? That's, you have to wait until then, and everybody will be using joint calculus. I mean, this is the same. Like for MapReduce, this was invented in Lisp at some point, and exactly 40 years later, Google has massively implemented MapReduce, and all this Hadoop thing took off, and for example, Erlang, same thing. It's the actor models in the 70s, and Erlang, and then there are all these lambdas. When were lambdas implemented, and when were lambdas added to most programming languages?
Yeah.
And then there are all these things that have become mainstream about 40 years after they were invented. It's weird. So joint calculus has a, well, 95, right? So it's about 10 to 15 more years to wait. Actor models, for example, is already mainstream. Data flow and all that stuff is already mainstream, but not joint calculus.
Well, then it's up to us to do that, eh?
There are a few projects that try to use it, like for industrial applications, workflow management.
Right. That sounds like a very logical place to do it, to use it.
Yeah. It's just that you have to start thinking in a different way, and that's always a problem for the software industry, because programmers don't like this. They don't like to completely change their thinking. It's hard.
But it's easier once you've made the transition. It's just a lot easier to think whether something is there or not, instead of like having to jump through these bloody hoops to do deadlock, thread starvations.
It's very difficult. You can have a lot of productivity once you start thinking in a new way. Functional programming is another such thing. It has been right now. It's kind of becoming mainstream. I had a graph of how many books were published in functional programming as a function of the year, and this is an exponential growth around 2015. Just exponentially larger number of books per year. And between 2015 and 2018, a huge number of books appeared with the title Functional Programming in X. And before, nobody cared. So that is,
programmers, it's getting into the mainstream. Programmers are starting to realize the benefits of functional programming.
Yes.
And I think it comes from like battle-hardened scenarios. Like, for example, Erlang, they arrived at functional programming because that's how, it's the most logical way to handle state in the face of failure. Well, maybe we the question mark about the joint calculus for the moment, but given the tools at the time, that was a very good way to do it, right?
Yes. Right. And functional programming can be formulated today. It's not just programming with functions. It's not just programming with immutable state in functions.
Right.
Today, it's a very specific toolbox that is being adopted by more and more languages. I mean, a lot of languages have functions, and if you feel like, you can make your values immutable. So, but there are things like summon product types, pattern matching on those. There are things like map reduce, map filter, reduce type programming, which goes hand in hand with Lambda, with nameless functions, with functions that are just written without declaring a name for them. So types with type parameters is another thing that is being adopted. Even Golang, Golang is decidedly, they wanted a simple language and they didn't want to have type parameters. Now they do.
Type classes.
Type classes. So it is
I'm still got
advanced.
a question mark. I've got more of a question mark about type classes. There's certain things there's certain things I've got a question about.
So there are all these other things in functional programming that cost to benefit ratio is higher, and then you don't want to invest in that unless you really have a clear demonstrated benefit. But those things that I just listed, map filter reduce, which is loop-free iteration without loops.
Recursion with
recursion, and some types now.
TCO, tail call optimization.
In my book, in my book, I call this a logic of types. But you said it was and or.
Okay.
Which is what I call logic of types in my book, which is the realization that you need these types in your language in order to be productive. and type parameters. And then after that, there are a few other things in functional programming that are harder to use.
Or nice to have.
Give you some, they're nice to have. Yeah, they give you benefits, but you could live without that.
Yeah.
So, but we cannot possibly live without these things. So these things are now in a lot of languages. Even Java is starting to put some stuff in there. And C++ has lambda functions.
The debauchery, whatever that is. Jesus, what is C++ nowadays? Good God.
Yeah, it's just because they're adding features because these features are so promising. Rust has pretty much everything that you need. Swift was designed from day one with this in mind.
Yeah, that was Chris Lattner's work. He's a well-experienced guy, that guy. So.
That's right. F#, again, it's designed from day one with this in mind. It's basically an OCaml light. So these are Scala. Again, was designed from day one with this in mind. So, and this is getting shipped to, C#, Python, and so on, in order to get more traction. But yeah, so that is what I wanted to add to functional programming. So there is a very specific toolbox which is not very large, but you can learn without learning any of the math, any of that stuff. You just learn how to use those things, and you are already a lot more productive. And people like me, they start asking questions about the math. But you don't have to, as long as you have assurance that somebody has asked and answered those questions.
And you can look them up. Yeah,
you could, in principle, ask, and that these questions have answers, and that is something that is quite special.
Well, Dr. Winitzki, thank you very much. I really appreciate this.
It was a pleasure to talk.
Good. Right.
Keep in touch.
Okay, mate.